All right, we're going to be talking a little bit more about limits. This is for paper 3 for a high-level course, in case you're wondering. But it still gives you a little bit of the basics of how L'Hopital's rule works. But first, just a quick review of some of the things that we've learned from limits before. We have the substitution technique. If you take the value that x is approaching and you just substitute it into the equation, sometimes it'll tell you what the limit is. So in other words, f of 4 could oftentimes be the limit as x approaches 4. In this case, however, we don't get that. We get 0 on the numerator and the denominator. And the question here is that supposed to be 1 or infinity or 0 or something else? And the answer is it depends. It depends on what got us there. And there's not enough information to tell what the limit is supposed to be when we end up with 0 over 0. Fortunately, we have these algebraic techniques. In this case, we can factor the numerator and divide out common factors to get a simpler equation, which can then be evaluated limit-wise using the substitution technique. So it looks like 0 over 0 equals 8 in this case, but that would be whatever this function is approaching when x approaches 4. Look at the graph of that in a moment. Here again we can see another indeterminate form is what it's called. It's basically infinity over infinity because both of these are parabolas. In fact, if I was being accurate, this would be infinity over negative infinity, which is still undetermined. Don't know what to do with that. So we try that other technique of dividing by the higher power. So you divide top and bottom by God, and you get an expression that's easy to limit. So we've talked about this in the past. But now there's this alternative, and it deals with situations that we just witnessed where there's an indeterminate form. And this is a guy named L'Hopital is credited with coming up with this idea, even though I don't think he originally did. But basically says, look, if you got a quotient of two functions, and both of them approach 0, or both of them approach infinity, then you have a candidate for L'Hopital. And basically, the limit of the quotient is equal to the limit of the derivative's quotient. So you take the derivative of the numerator and denominator separately, whatever the quotient that is, you take its limit, it'll be the same as the limit of the given function. It's kind of a weird trick, but it works. Important thing to remember, though, is these are the only conditions for which L'Hopital can be worked. So, as I observed earlier, these were both indeterminate forms. Now I'm going to take the derivative of the numerator and the denominator separately, and then you can see that as x approaches 4, we get 8. So the limit of the derivative quotient is the same as the limit of the original quotient. Do the same thing here. We take the derivative of the numerator, derivative of the denominator, and we allow x to approach infinity. Unfortunately, I see here we still have indeterminate form. So you can just take the derivative again. Numerator and denominator. Now you let x approach infinity. Well, it's unaffected by x now, so negative 4/3 is in fact the correct limit. And we learned that before. So you can see actually that thanks to this L'Hopital trick, these two functions, which I would probably use the squeeze theorem here and here, I don't even know what I would do, but in either case, now that we have L'Hopital's rule, if we can establish indeterminate form, which I have, infinity over infinity and 0 over 0, then we can use L'Hopital. So I will take the derivative of e to the x, which is e to the x, derivative of x squared, which is 2x, and still indeterminate, still infinity over infinity. So I do it again, e to the x over 2 this time, and now when I allow x to approach infinity, the numerator approaches infinity while the denominator stays at 2, so we have half infinity, or just infinity. In this case over here, we do the same thing, take the derivative of the sine as cosine, derivative of x is 1, and now we can let x approach 0 and get 1. Just one last thing in here, then I wanted to demonstrate how Wolfram Alpha will even do some L'Hopital for you, and it also evaluates limits for you as well. So if you can learn how to use Wolfram, it's a nice way to check your answers if Desmos is not available, or if you want something a little more concrete. So thanks for watching.